So today we're actually going to go back to solving equations, and these are going to be equations that have trig expressions in them. And basically the plan for today is I've got 5 examples that we're going to work through, and each example actually demonstrates a slightly different approach that you can take with these kinds of equations. So you're going to see these different possibilities. And I would say probably most of the equations you're going to see then for practice probably fall under one of these kinds of equations. So if you feel pretty comfortable with these 5 different approaches, you should be able to do just about anything that's on the practice or on a quiz or a test. So we're going to go through a few of them together. There are a couple of spots where I'm going to stop and ask you to figure one out on your own, based on what we've been doing, and just kind of go back and forth. We'll see a couple of examples. I'll ask you to try one on your own. We'll do a couple of examples. I'll ask you to try one on your own, and then we'll finish out with the last example. Okay? All right, so. Hello. There we go. First example. This is a little bit simpler type of equation, where we've got the sine of x plus the square root of 2 being equal to a negative sine of x. I would say that this particular type of equation and this particular type of method, which we're calling collect-like terms, is probably one of the more intuitive ones. Meaning that if I asked you right now to try to solve this, what your gut tells you should do is what we mean. So what's your gut tell you should do? What do you think the first step should be? If I said, you must give me a guess right now or you fail my class, what would you guess? Say again? And how would you do that? Okay. But remember, if I square the left side, because it's sine of x plus the square root of 2, I have to FOIL that. Right? It's not just a matter of sine squared and then square root of 2 squared. It's FOILing that all out. So does that really sound like what I want to do? No. What else? What are some other ideas? What would you do if you had to take a guess right now?
Add the negative sine x to both sides, set it to 0.
Okay. Because then all the signs are together, right? Similar to what we would do with any kind of equation. Usually we try to get all of our variables on one side together, and then we get all the numbers on the other side. And there's some exceptions to that rule, but a lot of times that's what we try to do. Well, that's what we're doing here. That's what we mean by collecting like terms. The like terms in this case are the signs of x's. So we want to get all of the signs of x's over on one side of the equation, and then get all of the numbers over on the other side. Okay? So if I add, excuse me, if I add this sine of x to both sides, then here I actually end up with 2 sine x's. Still have this plus square root of 2. And now this side, the sine x's are going to cancel out, and I'm left with a 0. Okay? So now all my sine x's are together. Now I want to isolate it. So I need to get all the numbers over to the other side. So what should I do first to move numbers?
Wait, so you want the square root to be by itself, right?
I want the sine x to be by itself. Because the square root's just a number, right? I want to get that variable by itself. And it's inside of sine, which means I probably need to get sine by itself.
Divided by 2.
Should I divide first?
Subtract the square root.
Yeah, subtract the square root of 2 first, then do the dividing by the 2 that's on our sign. So subtract square root of 2 first. So that leaves us with 2 sine x equal to negative square root of 2. Then divide both sides by 2. And I end up with the sine of x equal to a negative square root of 2 over 2. Look familiar? Square root of 2 over 2? I hope so. Because that's one of the answers from the special angles on our unit circle. Right? Square root of 2 is one of those answers that we can get. And most of the answers that you're going to get from your equations are going to be that way. You're going to be given equations where when you get to this point and you have a trig expression equal to some answer, they're going to be answers that you should be able to figure out from the unit circle, and you don't necessarily need to have a calculator. Okay? So, how do I figure this out? Well, you might look at this, and based on what we talked about last chapter, go, oh, look, we can use inverse sine now. Because I'm trying to get x, right? So if I'm taking the sine of x equal to this thing, getting rid of sine so that I just get the x by itself would be inverse sine. We finally get to use it. Well, sort of. We made a really big deal last chapter about the fact that when you take inverse trig, you have a limited interval on what you can get the answer for. Well, basically, we go through that, and we go through all of that pain and agony to explain to you why the calculator works the way it does, to be honest. Calculators can pretty much only function on functions. So if you're going to you're going to program in how to do an inverse sine, it has to be an inverse sine function. Which means if I put in negative square root of 2 over 2, I can only get one answer out of that because it's got to be a function. So in that context, I have to limit where my answers can come from so that I can make it a function. But when you're doing things like this, where you're supposed to be solving an equation that has these trig functions in it, the limitation is not that big a deal anymore. The limitation sort of tells you where to start, maybe, but you don't want to stop there. You want to come up with all the possibilities. And if we just leave the problem as is and say, hey, I want you to solve this, then we have to actually think about, okay, so on the unit circle, I can go around and around and around as many times as I want to. And every time I get to an angle that's a possible answer, I would have to include it. Well, that gets kind of messy too. I mean, we can do it. Pre-calc's going to have to next week because they're just about ready to do this similar lesson. But at this level, in advanced algebra, I'm not really interested in that either. I don't care that you can give me every single possibility. What I care about is that you can give me what the solutions are. Whoops. One rotation around from 0 to 2 pi. And notice we're including the 0, but we're not including the 2 pi because 2 pi really just brings you back to 0. So when you see this, when you're asked to solve an equation and they give you this interval, what that basically says is on one rotation around the unit circle, what would be your solutions? We don't have to worry about lots of rotations and all of the possible solutions. We just want to know on one rotation around, what would your solutions be? Okay, and that's what all of our problems are going to be asking you for. So let's think about the unit circle for a second. If I'm asking you to solve for x here, first of all, what does my variable actually represent in this problem? What kind of answer am I trying to find? So I'm taking the sine of x and I'm saying it's supposed to give me a negative square root of 2 over 2 for an answer. What kinds of numbers does x represent? What do we have to take sine of? What kinds of numbers can I take sine of, or cosine of, or tangent of? Angles, yep. So when we're trying to solve these, we have to be thinking about what angles make this true. And we're going to be back in radian measure now. Excuse me. So usually when we solve equations, we're solving for radian measures, and we give our answers as radians. So when you've worked it out to this point, and you've got, sorry, the sine of x equal to negative square root of 2 over 2, what you now need to figure out is, what are the angle measures that if I take the sine of them, I'm going to get the negative square root of 2 over 2. So the first thing I recommend that you kind of think through is, well, which quadrants would they have to be in? If this is supposed to give me a sign that's negative, what quadrants would I have to be looking at? 3 and 4. So I know I have to come up with angles that are in those two quadrants. Okay, because that's where sine is negative. Okay, then think through your reference angle. So what's the reference angle that would give me square root of 2 over 2? Pi over 4. Right? Sine square root of 2 over 2, that's the pi over 4. So if pi over 4 is my reference angle, then what's the related angles in the third and the fourth quadrant? What's the corresponding angle in the third quadrant if I have a pi over 4 reference? Five pi over 4. And what's the corresponding angle in the fourth quadrant if I'm using a pi over 4 reference? 7 pi over 4. So guess what, ladies and gentlemen? We can't throw away the unit circle yet. All that unit circle work we did last chapter, we need it for this. Because we need to be able to narrow down what quadrants are we going to be talking about that these solutions would be in, and then based off of reference angles, what actual angles give me solutions to this equation. So if you're rusty on that, I suggest you go back and do a little work on that over the next week, because we don't have class again until Monday, so you got lots of time to get back on track with that if you're feeling a little rusty. Okay? So ultimately our solution should be 5 pi over 4 and 7 pi over 4. Now, one thing I would recommend is that you check your answers. Because let's face it, if we're trying to solve equations with trig functions in them, they're going to be a little funky. And we may not feel 100% confident that we did it right. Okay? So, obviously, one way to check is to plug them back in for x and solve it out algebraically. But if you weren't that comfortable with the algebra to solve it in the first place, you might not be that comfortable with the algebra to check it. So algebra may not be your best option. So you can also check things graphically. And I just want to show you really quick what that looks like and what you're looking for. And I actually want to even suggest where you might do this. Man, sorry guys, I've got some crud in my throat. So if we go to graphing here for just a second. Instead of your TI Inspire, I would actually recommend this website called desmos.com. DESMOS. Because one of the few things that I don't think the Inspire does very nicely is label your graph for trig functions. Like you can go to your window settings and you can say that you want to, you can actually type in that you want to go from a negative 2 pi to a positive 2 pi. But when your window actually comes up, they always change it into what the decimals are. And so even though you've said, I want my tick marks to be at, pi over 4, you always get the decimal equivalent for what that is. And that's not real helpful when we're trying to give radian answers in terms of pi. If you go to Desmos, you can set it up to actually give you your axes labeled the way you want. So the way you can do that, if you go to, let me just start over here. If you just type in the desmos.com, you're going to get a page that looks like this. Okay? You can launch this calculator without having to have any kind of an account. Now you can have an account. An account allows you to save things. It allows you to print things off. But as a student, you probably don't need those things. That's something that's helpful for me as a teacher. Okay? So you don't have to have any kind of account. You just click on the Launch Calculator button and you go. And so to set it up for trig, you go up here to the little wrench, which is where you have your graph settings. And I want my x values to represent radian measures. I've also already said that I want to keep my answers from 0 to 2 pi. So the first thing I can do is right here, where it's currently set negative 10 to 10, I can make that 0 to 2 pi. And remember, the pi symbol is just option P. So that will adjust how much of the x-axis I'm going to look at. And then here for step, the step represents where my tick mark's going to be. So maybe I want my tick marks to be every pi over 4. So I can actually type in option P for pi divided by 4, and it will set up my x-axis as multiples of pi over 4, rather than changing them to some decimal. Okay? And then my y values can stay that way, that's fine. I'm in radians, that's good, that's what I want. So now for the actual graphing, you just want to take each side of your equation that you started with and set it up as a separate graph. So one of my graphs is going to be sine x plus square root of 2. My other graph is going to be negative sine x. So y equals, I can either type sine x, I have to put x in parentheses, and then plus square roots right there, 2. Okay, hit enter, there's one of my graphs. Or the other way is here in the functions button, one of the categories they have here is trig, so I can get my sine that way. Okay, so now what should we be looking for to tell where the actual solutions are? The overlaps, the intersection points. And notice that when I get to an intersection point, what comes up is the ordered pair with the x coordinate as a radian in terms of pi. So it's way easier to match up with what I got for answers to see if I'm right. And if I really want to see it, I can actually click on it and it'll make it darker, and then it'll stay. If I move my cursor away, it'll stay there. So there's one intersection point. There's the other intersection point. What are the x values in those 2 points? Which is exactly what we said the solution should be. So the first time you go into Desmos for a particular assignment, you're going to have to set up your x-axis the way you want with the radian measures, whatever. That takes a couple of minutes. But once it's set up, actually putting your equations in and checking your answers is really easy. And Desmos is really nice about giving you actual radian answers in terms of pi, rather than as decimals that you have to go, well, is that the same or not? Or I don't know. Yeah.
Do you need it in a calculator?
No. All you have to do is just hit launch calculator and it'll go. You can, like if for some reason you want an account, you want to save graphs or print graphs, whatever, you can get one, but you don't need one. Okay? All right, so I would highly recommend that as you're doing these at home, bring up the Desmos.com on your computer and be checking them as you go. Make sure that what you got for answers algebraically match up for what you see graphically. All right, example number 2. Taking square roots. So as we've seen, it's not uncommon for our trig functions to be squared. So that can happen in our equations as well. We may have something like what we see here, 3 tangent squared x minus 1 equals 0. So again, I would say this one's probably pretty intuitive. What do you think we should do to get to x? Add 1 to both sides. So that leaves me 3 tangent squared x equal to 1. Then what? Divide by 3. So now tangent squared of x should be 1/3. And then what? Take the square root, right? Thus the name, taking square roots. At some point, if you have trig functions being squared, you're probably going to have to take square root of both sides to get your answer. Okay? When I do that, I'm going to get the tangent of x equal to what? Yeah, thank you. That's the biggest thing to remember about this method. Is it just like any other equation, if I take the square root of both sides, I have to have the plus or minus of my result. And then if I'm taking the square root of a fraction like this, I want to make sure that I rationalize it. Because this should look familiar. Square root of 3 over 3 is again one of those results we get from the special angles when we take tangent. So now I'm ready to try to identify what are the angle measures that actually make this happen. So what quadrant should I be in this time? Is that it? All of them, right? Because this tells us that my answer to tangent can be either positive or negative. So that means I can use all of the quadrants to get an answer because positive or negative should work. Okay? So now I need to decide the reference angle. What's the reference angle that gives me a tangent of square root of 3 over 3? Ooh, I see a lot of reviewing coming up this week. What's the reference angle that's going to give me a tangent of square root of 3 over 3? There's only 3 options, because we know the axes are kind of weird ones, right? So we got pi over 6, pi over 4, or pi over 3. Which one's going to do it? Pi over 4? So what's the sign of pi over 4? Square root of 2 over 2, right? What's the cosine? Square root of 2 over 2. So if I take square root of 2 over 2 over square root of 2 over 2, am I going to get square root of 3 over 3? Okay, so now we're down to pi over 6 or pi over 3. Which one's going to do it? Pi over 6. So sine is 1/2. Cosine is square root of 3 over 2. So if I do my invert and multiply, I'm going to end up with 1 over square root of 3, which I have to change into square root of 3 over 3. Okay, so pi over 6 is my reference. All right. So pi over 6 is my reference, and I can have angles in all of the quadrants. Then what should my values for x be? Pi over 6 is a good start. That's my first quadrant angle. Not quite. Because 4 pi over 6 is going to reduce to a pi over 3 number, right? So I don't want 4 pi over 6, I want 5 pi over 6.
So you don't want any numbers that can reduce to any numbers.
Right. Because if I can reduce it to something else, then that means it's got a different reference angle. Right? It means the denominator is going to change, and that means the reference angle is something else. Okay, so 5 pi over 6. Here's my pi over 6. Here's my 5 pi over 6. What would be my third quadrant? 7 pi over 6. That's going to be about right there. And then fourth quadrant. That's the one about right there. So I'm going to end up with 4 different possibilities in this case, because when I took the square root, I could get positive or negative answers, which means all 4 quadrants were possible. Okay? And again, it didn't say it specifically, but we're assuming with all of these, unless you're told differently, that we're just looking for solutions from 0 to 2 pi. So 1 time around the circle. Okay? And again, if we do a quick check, this time, since our equation was equal to 0, I don't really need the second equation. I'll just look for where the x-intercepts are. So 3 tangent, show the keyboard here, squared of x minus 1. I've got one right there, right there, right there, and right there. How'd we do? Is my graph supporting what I got algebraically? Yep, pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So that's a good sign. That means we're brilliant and we know what we're doing. Okay? Questions on these first two? All right, then it's your turn. So multiple choice corners means this. I'm going to give you a minute to work out this equation. You have 4 choices here for multiple choice as to what you think the solution should be. Each of your choices, A, B, C, and D, corresponds with a sign that's up in a corner. So we've got A up here beside me, then B's back there in that corner, C's back by the door, D is up here by the front door. So in a minute, once you've had a chance to work this through, I'm going to ask you to pick A, B, C, or D, which one you think is correct, and you're going to get up and move to that corner as a way of saying, I think this is the correct answer. Okay? It's just a quick little way of kind of getting up and moving around a little bit. So take a minute, work it out, see if you can get answers, and see if you can get answers that matches one of your choices. But don't move to your corner until I ask you to. Give everybody a chance to think. All right, you got a choice? All right, get up and show me. Go to your corner. A is up here, B's back there, C, D. Just mean you're staying in that corner? Or? Okay. Schaefer, you got to pick?
No.
All right. Morgan, can you tell me why you picked corner D?
Because you square rooted it, so it had all 4 components. That's why I did it.
Okay.
The plus and the minus.
So as you work this out, what's the first step you probably did? Subtract the sine x from both sides. When you did that, it ended up canceling them both out. So now you're left with 2 sine squared x minus 1 equal to 0, right? Because you subtracted it. So now if we try to get our sine squared by itself, we're going to end up with sine squared of x equal to 1/2. So we had to add the 1 to divide by 2. And then when we do our square root, we have to remember that this is going to be plus or minus the square root of that 1/2. So if this were a question on like an ACT or SAT or PSAT kind of test where it's multiple choice, that alone should tell you it's got to be D, because just like Morgan said, if it's plus or minus, then that means there should be an answer from all 4 quadrants. So if the only choice with 4 answers is D, I'm done. Now, our quizzes and tests aren't multiple choice, so you would continue working this out and say, well, that really means that the sine of x is equal to plus or minus square root of 2 over 2. That looks familiar. Plus or minus means I want all 4 quadrants. Square root of 2 over 2 means pi over 4. So pi over 4 is going to be my quadrant 1 angle. 3 pi over 4 will be my quadrant 2. 5 pi over 4 is going to be my quadrant 3. Whoops. And 7 pi over 4 is going to come from my quadrant 4. So all of the 4 denominator angles that would have pi over 4 as its reference, those are the ones that you want for all of your possible answers. Okay? Make sense? Does that help, Schaefer? Okay. All right, go ahead and have a seat again. So those first 2 examples, I would say, are quite a bit intuitive. Like once you've seen a couple, you're kind of like, oh yeah, that makes sense. Get all the trig functions on one side and then try to get the trig function by itself, and maybe we have to square root both sides when we do that, and make sure you get plus or minus if we're going to square root. Okay? The next 2 examples, yeah, go ahead.
I did sine x equals plus or minus square root of 1 over 2 get changed to plus or minus 2 over 2.
Because technically, when I take the square root of a fraction, that means the same thing as taking the square root of the numerator and the denominator separately. And I can't have square roots in the denominator. So I had to multiply the top and the bottom by that square root to get rid of it. Which means on the bottom now, square root of 2 times square root of 2 just leaves me with 2. Square root of 1 is just 1 times the square root of 2 gives me the square root of 2 on top. So this is just the result of rationalizing this. Okay? Getting rid of that radical from the denominator. Any other questions? Oh. Excuse me. All right, next example. The next 2 may seem a little less intuitive. Okay? Excuse me. So if you take a look at this equation, where we have the cotangent of x times cosine squared of x equal to 2 cotangent x. What do you think the first step should be? It seems like a good move.
Divide by cotangent x.
Okay, so it looks like I could divide both sides by cotangent x, yeah? That seem reasonable? That's where it's not intuitive. Because that's what we all want to do, right? We all will look at that and go, oh look, cotangents on both sides. Let's cancel them out. The problem with that is that your cotangent of x has x in it. It has a variable in it. And if you divide by anything that has a variable in it, you run the risk of losing solutions. Okay? So it means you've basically canceled out one of the variables, which probably represented one of the possible solutions. And that's bad. So, instead of dividing both sides by cotangent x, we're actually going to kind of go back to what we did in the first example, and we're going to gather everything on one side. We're going to collect the cotangents on the same side. Okay? So I'm going to go with cotangent x times cosine squared x, and then I'm going to subtract the 2 cotangent x and make that all equal to 0. Okay? And now, I have a common factor. So the thing that you saw as being the same thing on both sides, well, now that I've moved it over to be on the same side, instead of seeing it as something to cancel, it's now becoming something to factor. Because it's now the common factor in both of my terms. Okay? So if I factor that out, then what's left? Just?
Oh, no,
Cosine
cosine
x
x.
minus 2.
Yeah, so we've got the cosine squared x from this first term, and then the minus 2 from the second term. Okay? Now, that helps us because now we are looking at a zero product property situation. Just like we do with quadratics, where we get everything on one side, set it equal to 0, and then we factor it, and then we set each factor equal to 0, because the zero product property says if I multiplied two things together and ended up with 0 as an answer, only way that can happen is if one of those two things was a 0. Okay? So that's the situation here. That is not just for quadratics, that's for anything. If I've got two things I'm multiplying together and ended up with 0 as an answer, one of those two things had to be 0. So by setting this up as two factors that are now equal to 0, just like with quadratics, I can set each factor equal to 0 separately and solve it from there. Okay, now for the cotangent one, it's probably easier to think about your solutions if you think of it as cosine over sine. So when am I going to end up with cosine x over sine x equal to 0? Forget about actual values of x for just a second. What's going to have to be true in order for cosine of x over sine of x to end up giving me 0 as an answer?
Cosine of x is 0.
The cosine of x has to be 0. In order to end up with a 0 answer from a fraction, I have to have my numerator be 0. Okay? So that's really what we're thinking about then. When will cosine of x be 0? Is it going to happen in quadrants or on axes?
On axis.
On axes. So we got to figure out which axes we're on, right? So is cosine related to the x or the y coordinate? X, right? When I put the fingers down, the cosine's always the one that's over here as the x coordinate, sine's over here as y coordinate. So when do I have x's that are 0? Where would I be if I have x values that are 0? On the y-axis. So as I rotate around, the first time I get to the y-axis is here. Whoops. Couldn't get this yet. Here we go. Is right here. What angle is that? Pi over 2. If I continue rotating around, the next time I get to the y-axis is here. What angle is that? 3 pi over 2. So those are two solutions from the cotangent x being equal to 0. Pi over 2, 3 pi over 2. Okay? Now we're going to come over here to our second factor. I'm going to add the 2 to both sides. And then I'm going to take square root. So I want to figure out, when does cosine x give me plus or minus square root of 2? Now, there should be little alarms going off in your head right here. Because when you think about the special angles on the unit circle, did we ever have any that were just square root of 2? No, we had square root of 2 over 2, but we never had any answers that were just square root of 2 for cosine. So that should already be making us kind of suspicious. Like, wait a minute, what's going on here? And if we actually dig into this a little bit more, what is a square root of 2 equal to approximately? Square root of 2, what's it equal to? It's about what? Give me a decimal.
1.4.
It's about 1.4. So I'm trying to say here that I need a cosine of x to give me an answer that's about 1.4. So think about your cosine of x graph. How high was cosine able to get? How high?
Very high.
For just cosine x?
2, 1.
To 1, right? How low was cosine x allowed to get to?
Negative.
-1. I'm trying to get a 1.4. I don't think that's possible. Because I've gotten rid of all the numbers, so there's no amplitude to stretch it out, there's nothing to make it funky. I'm just looking at a plain old cosine x. And for plain old cosine x, I have to get answers that are somewhere between -1 and +1. -1.4 and +1.4 are out of that interval. So what that tells me is that this factor doesn't give me anything. Because it's not possible. So the only possible answers I could get are those two right there. Now, just to prove my point about not canceling, what if we had gone up here, back where we wanted to, and we canceled out that cotangent x? What if we had done that?
No solutions.
Yeah. Then we would have ended up with cosine squared of x being equal to 2. We would have taken our square root of both sides, and we wouldn't have gotten anything to work. So we would have said there's no solution to this. Nothing makes this true. So here's a perfect example of why we don't want to divide by anything that has a variable in it. Because if we do, we might lose possible answers. And that's exactly what would have happened if we had divided by that cotangent x. Okay? And again, if you wanted to check, you can go to your graph on the Desmos. You can put in the cotangent x, cosine squared x for one equation, put in 2 cotangent x for the other equation, find the intersection points. It's going to be at those 2 points. Okay? Example 4, the quadratic type. So this one is one of those where you look at it and you're going to kind of go, ooh, this kind of looks familiar. I've got a first term that's being squared. I've got a middle term that's not. And I've got a third term that's just a constant. I've seen this before. It's a quadratic. Oh, but wait a second. There's those signs of x's in there. Is it really quadratic? It's technically not quadratic. But it kind of fits that form. So that's why we call it a quadratic type. It's got that look of being a quadratic. Which means we should be able to use some quadratic method here to help us figure it out. But for some people, seeing the sign of x in there while they're trying to deal with it as a quadratic just makes their little brains go like, I can't deal with that. There's quadratic, there's trig, there's like, what? So, this is another great place to use U substitution. I think we talked about this a little bit before, where if something kind of looks like something you know how to do, but not quite, we can do the substitution to make it look easier. So we can do U substitution in this case to make it look like just a quadratic. So we can deal with just the quadraticness of it. And then we can come back and deal with the trigness of it, rather than trying to deal with both at the same time and having our little brains explode on us. Okay? So by substituting sine of x with a u, I now have an equation that looks like this. Can you deal with that? Yeah, now it's just quadratic. We've been doing those for 2, 3, 4 years now. Okay, so let's deal with it as a quadratic. What can we oftentimes do to solve a quadratic? Factor. So can I factor 2u squared minus u minus 1?
Yes.
What would it be?
2u minus 1 and u plus 1.
Okay, so let's just FOIL back out, make sure. 2u and u are going to be 2u squared. 2u times 1 is 2u. Negative 1 times 1 is negative u. Uh-oh. That didn't quite work. My lasts are good. Negative 1 times positive 1 is negative 1. But how am I going to fix this to make this middle term work?
Change the u into u.
Right? So now we've got 2u squared, negative 2u, positive 1u. So now we've got that negative u we need and still have the negative 1 there. Okay, so double check that your signs are all going to work out okay. Okay, so if those are my factors, then from this first factor, what could u be equal to? Negative 1/2. And from the second factor, what could u be equal to? A positive 1. Okay? So I have solved the quadratic part of this problem. But I wasn't asked to solve for u. My original equation had x's in it. I was asked to solve for x. So now I go back up here and I say, all right, so instead of u, what I really want to know is what's going to make sine of x equal to negative 1/2? And what's going to make sine of x equal 1? So now I'm bringing the trig part back into the problem to finish things out. Okay, so thinking about our unit circle again. If I want sine of x to give me a negative 1/2, what quadrants would I have to be in? 3 and 4. Those are negative signs. What is the reference angle that's going to give me 1/2 for sine? Pi over 6. All right? 1/2. Or 1, yeah, 1/2. Okay, so I need angles in quadrants 3 and 4 that have a reference angle of pi over 6. So what's the third quadrant angle? 7 pi over 6. What's the fourth quadrant angle?
11 pi over 6.
So those are the two possible solutions from the first factor. Now, what about my second factor? For what angle do I get a sine that is 1? Pi over 2. Because I need sine, which is related to my y coordinate, to be as big as possible. So that's going to happen here when I'm on the y axis. Excuse me. So pi over 2 is the possible solution from that factor. So all three of these then make up the possible solutions. 7 pi over 6, 11 pi over 6, and pi over 2. Okay? So, keep this in mind as an option. When you have something that kind of looks like it's quadratic, but it's got all that trig stuff in there, if the trig stuff is messing with you, substitute the u in, take the trig stuff out, work it as a quadratic, and then bring the trig back in and finish it out. Okay, that can be a lot easier. If you can do it with the trig stuff in there, fine. But if that's messing with your head, take it out, work it out as the quadratic, then put the trig back in and finish it out. Okay, questions? All right, it's your turn again. Two cosine squared x equals cosine x. Decide which of those is going to give you the right set of solutions. Think you got it? Ready to pick? Yes? No? Maybe? The overwhelming responses. Are you ready to pick? Nuh-uh.
Yeah, but I don't know what to do after I read it.
Yeah.
So what do you do first?
Minus cosine x.
Minus the cosine x. Remember, you cannot divide by cosine x because there's a variable in it, right? So we're going to minus it. What can we do from there? We can factor out the cosine x. That's going to leave a 2 cosine x minus 1. Right? So that means we can figure out when cosine x should equal 0, and we can figure out when 2 cosine x minus 1 should equal 0. Which means this is when cosine x, got the x in there, should equal 1/2. Cosine x equals 0. Pi over 2. Okay. Only.
And 3 pi over 2.
So that right there gets us down to either C or D. Oh, no, I'm looking at the wrong thing. Gets us down to D. Because it's the only one that has 3 pi over 2 as an option. Now if we continue and we figure out this one as well, cosine being positive means we have to be in the first or the fourth quadrant. And for 1/2, cosine means I'm looking at pi over 3. So pi over 3 would be my first quadrant angle. And then 5 pi over 3 would be my fourth quadrant angle. So this is the total set of solutions. Pi over 2 and 3 pi over 2, pi over 3 and 5 pi over 2.
Wait, sorry, I didn't really get the cosine x equals 0 part.
Cosine x equals 0. We did that a minute ago. We said cosine was related to x. So when is x going to be 0?
Y-axis.
On your y-axis. So when do I get to the y-axis? At pi over 2 and at 3 pi over 2. Okay? Okay, I don't want to go through the whole thing, but just one more quick example. What happens when I have something that kind of looks quadratic, but yet my two trig functions are different? So I can't really use quadratic on it. What I need to do is go back to the identities. And I have to go, well, instead of using sine squared here, what if I change that with 1 minus cosine squared? Whoops. Then I can distribute the 2, I can combine what I can combine, and I get cosine squared, cosine constant, and it's going to be a quadratic looking type problem, but now with all cosines rather than having different things. So just keep that in mind for a couple of them, that sometimes you may need to go to your Pythagorean identity and switch something out if what you have doesn't quite fit. Okay? But once you get that worked out, substitute it in, it ends up being like a quadratic, which you just did. So, all right, that is actually our last lesson. So heads up for a quiz next class, which is actually next Monday. So you got plenty of time to get through the homework and look at the practice quiz and be ready for a quiz on Monday. Okay? And then we'll finish up with a test on next Wednesday. So heads up on what's coming up there. Make sure you're ready. See you next week.